Thanks, Nuno. Thanks for inviting me here, and thank you for coming here. It's such a nice day, and you came here in spite of this very generic title that, when now I read this title, I'm wondering why anyone would come here for such a generic title. There will be specific things to this talk, not just. All right. So I have a slide which sort of ties together what I'm going to talk about and explains a little bit the title. What I have here is a list of integrated circuits, and there's a few things about them. None of these are particularly novel circuits, with perhaps the exception of some of the sensors here. Some of these are old circuits. But there's a couple of things which are very important for the points I want to make, which is that they have fairly good computational power. I mean, you see there the Texas Instruments microcontroller there, 16 megahertz, 16-bit architecture. What's also surprising about one of these things I took the trouble to put is to put you the prices. So that particular microcontroller costs 39 cents. And it's a RISC processor, 16 megahertz. You can do a lot of computation with that thing. The other thing that's not there, now I realize I forgot to put, which is the power consumption. If you don't do much with it, you can run that on a AAA battery for a month. If you really don't do a lot, a year. There's a lot you can do with that. The second one you have is a Raspberry Pi. You may have seen about that. If you want to buy one, it costs you $20. And it's a computer. It's a wonderful computer. You can do really sophisticated stuff. It even has a GPU. So that's in terms of computation. I put here a couple of things on wireless communications or wired communication. And again, the point is the energy consumption is very little. Of course, when you do wireless, you always spend some energy communicating, and that's going to be something I'll be talking about later. But they're also very cheap. And sensors also, I just took here some examples, very, very cheap things you can buy. And especially the fact that you can have very cheap computation, communication, and sensing allows you to design control architectures very different from what we teach in the basic undergraduate and even graduate control classes. We have these computer diagrams where we write a process, a control, maybe a process, we put a sensor, a controller, we put some lines, and those lines we imagine wires going from the sensor to the controller, and the controller then to the actuators. But in fact, what you can do with this is construct these very small modules where you connect a sensor with one of these microcontrollers and a network controller, and it will cost you, a fraction of $1 if you want, if you're doing it in quantity. And you can connect that now with your controllers to a shared network. And the same network can then be used to connect the controller to the actuators. And all you need is to have a couple of twisted wires going, for example, in a car or something like that, as opposed to having dedicated wires between every sensor, every controller, actuator. So what this allows is you can build systems that are very cheap, very inexpensive, very flexible, because adding a sensor and actuator means almost nothing. You just connect something more to an existing bus. Very easy to deploy, expand, etc. And they can be fairly intelligent, right? Because one of these processes, they run at megahertz. They do computations on the scale of microseconds. So you can do things very sophisticated, paying almost nothing. And this talk is to use this as a starting point to point out a couple of problems, theoretical but also practical, that come out of this type of architectures, right? So the talk is going to be divided in two parts. The first part, I want to talk mostly about the implications of having networks, shared networks, to mediate the communication between elements in a control loop. That's going to be the first part talk, so focusing on the communication part. The second part, because I also wanted to do that, I want to talk a little bit about opportunities and challenges too, that arise from the fact that now you have these nodes that you can have controllers that do computations in microseconds. So if you do computation on the scale of microseconds, and maybe you're sampling your system at 1 kilohertz, you have 1,000 microseconds per sampling time. So that's a lot of stuff you can do, right? So that also opens the opportunity to consider control algorithms that actually make use of this. Instead of just having these processors, you still pay your 39 cents, but the process is basically doing nothing all the time. Right? You might as well do something interesting. So that's the second part of the talk. So network control systems. So network control systems, see where I have my, here it is. So the idea behind network control system, I sort of described to you this picture. You have some shared network, which could be wired or wireless. And you have several elements that are part of your control loop, controllers, sensors, actuators, and they all share this network. Network control systems are quite common. I started to be interested in them because of applications in this area, and so I was doing control of robots, mobile robots, and there actually I didn't have a choice whether or not to use a shared network or not, because if you have a mobile robot, you have to communicate. If you want to communicate one mobile robot to the other, it has to be wireless. So wireless is a shared medium, so there was nothing I could do about it. At this point, it wasn't even very cheap to do the wireless communication. When I started on this, it was before Wi-Fi, so it was not so easy. This is also an application that in particular, one of my students worked quite a lot, which is automotive industry. It turns out that probably as late as 10 years ago, there was, well, it wasn't exactly 10 years ago, but starting perhaps 10 years ago, there was this change towards dedicated communications in cars to shared networks. And now, essentially any car, no matter what price range you're looking at, all the elements in the car, all these ECUs, electronic control units, communicate through a network, most likely a CAN bus. And basically all these wires that used to exist inside the car, you'd open the hood or you look at what was inside the door, and there was this big bundle of wires, they all disappeared, and now there's typically a CAN bus. So this is an area where there was probably, if you go and look at consumer market for network control systems, there you'll find the most sophisticated things, cars. And then there's other areas which I haven't worked directly, but they're important, is for example in process control, and the problem in process control is that if you go to any sort of process control facility, the number of sensors in the actuators is on the order of several hundreds of thousands actuators, and so you have to manage that somehow, and so that's a place where you'd want to have networks to communicate. And the other ones are smart buildings. I had a student that worked on that, but I haven't worked too much. But once again, you have lots of typically sensors and also some actuators. For example, in the HVAC system, the heating, ventilation, and air conditioning system, and you want those networks. So I'll tell you a little bit about these network control systems. I guess the message of this slide is that these things are everywhere. In fact, now it's probably very rapid. It's going to be more difficult to find a control system that's not a network control system than otherwise. Okay, so why should I, as a control designer, care to know whether or not my connections between a sensor and a controller go through a shared network as opposed to a pair of wires? Because when I teach undergraduate control classes, I don't really care too much. I just draw these lines between sensor and controller, and I don't care what's there. So this is an example, not from my work, that shows that. So this is the control system of a car, is the active suspension control system. So you have the 4 wheels, and you have some actuators at each wheel. And if you want to think about it in terms of a network, so you have the 4 wheels here, that's the nodes 5, 4, 6, and 7. In each wheel you have the actuator, and you have some sensor. And then you have a controller, it's another node. There's total 7 nodes. The other 2 nodes are, you have a roll and pitch sensor, and you have a heave position sensor, measures the acceleration, the vertical acceleration. And the control system is to basically try to keep, when the car hits a bump on the road, trying to prevent it from jumping too much, right? You want to minimize accelerations. This uses a control area network bus, and this is a particular protocol. It's a collision-free protocol. Every node has a priority, and if 2 nodes want to talk at the same time, there's a clever mechanism to make sure that they will not collide. One of them wins and transmits the message, the other backs off without a collision. It's fairly easy to do this in a wired way. So what it's done is each node has a certain priority. right? And what you see are two simulations of this system. Time axis year, and year is vertical acceleration after the car hit a bump on the road, right? And you see two completely different behaviors. There's a green one where the acceleration, eventually went back to zero, the car recovered, and then you have an unstable behavior, which is the red one. The difference between these two simulations is very small. It's the same system, same controller, same disturbance. The difference is in the priorities you gave to the nodes, right? You always, in this particular protocol, you have to decide the priorities. The green simulation that work best, small numbers mean high priority in CAN. You gave the top priority to the controller, and then to the two sensors, and then came the four wheels. So if there was a collision, the controller talks first, followed by the sensors. In the red simulation, you gave priority, it's a little bit arbitrary, you gave priority to one of the wheels, and then you kept all the priorities the same, right? Same numbers, you just shift them all, you give the wheel. And that's the difference between stability and instability. Right, so obviously if you ignore the network, you design the system thinking it's going to be stable, and then you implement it, and someone decided on the priorities, and it just doesn't work. And it's not obvious why giving a priority to the wheel is a problem here. Now, there's something about this which I should just clarify. To get such a sharp contrast between the two, we were working close to the capacity of the network. None of the simulations, this is the same simulation, same everything equal, they're both below capacity. So this network CAN bus can go at most 1 megabit per second, but in cars actually it's a different version of the protocol. I think it's like 150 kilobits per second. So we were sampling all the sensors below capacity, but close. Instead of 150, maybe we were at 130. All right? And what's going to happen is that when you're close to capacity, sometimes you create you don't create collisions, but one node has to wait for the other. And if you're close to capacity, that can introduce delays that eventually destabilize your system, right? So the purpose of this slide once again is to convince you that one needs to look at these systems. And I should also say there's good reasons to work close to capacity. Of course, one way is not to work close to capacity. In the case of this particular CAN bus, that means don't make your car more sophisticated than 150 kilobits can do. And in fact, that's not possible in trucks. And so I have not worked in trucks, but people in trucks actually have all sorts of complicated things. They put multiple buses because in trucks, these networks just don't have the capacity for it. All right, so let me now start talking a little bit about modeling and how do you understand. So what I'm going to do is to show you one particular model, network control systems, that allowed us to make some progress in this area. And this is going to be a particular type of hybrid systems called stochastic hybrid systems. All right. Instead of starting directly with the model, I'm going to give you sort of a very prototypical problem in network control systems that explores these issues, the problems that arise because of using a shared network. So this picture is, this top part is more or less standard. You have a controller and a process. They are connected by these lines. When I just connect them by a line, I'm imagining that's just a dedicated line. There's no collisions. You don't have to worry about delays. It's the standard stuff. And so what this would mean is that somehow your controller is close to the process and talks to it directly. But the sensors are not. So here you have two sensors that measure this state here. This could be, for example, a vector with two components. For example, and one sensor measures one component, the other measures the other one. And they have to send this information to the controller through a network. And this very simple model, what I'm imagining is that the sensors are going to take turns. So let's see where it is. In odd instance of time, sensor 1 sends a measurement. And then on the even instance of time, sensor 2 sends a measurement. And the way this works is that you have hold 0 on this side, and when a measurement comes, you update the state of the hold. You keep the other one unchanged, vice versa. I think it's fairly easy to understand. And then what comes out of this hold is sent to the controller. So the controller is going to see these sort of piecewise constant signals that where the stairs discontinuities appear at different instants of time. If you had a linear system, this is your process and this is your controller. Well, this would be the equations. There is another dynamic element here that one has to keep in mind, is these holes, right? That's where the memory is. And one simple way to model that is to say that this y hat, which has two components, has derivative 0, except when there's an update. Right? When there's an update, these guys are going to have discontinuities. And if it's an odd instant of time, this measurement comes. So there's going to be a discontinuity in the y1 hat, and you see here the equation says y1 hat at time tk when k is odd is going to be the value of y1, the true output coming. Right? So discontinuity, you adjust the y1 hat to y1. At that time, nothing comes through the second sensor, so this is continuous. The minus is the limit from below, and you just keep that state continuous. Then at the even instant of times, you change that. So you see that this part of the state varies in a continuous fashion, and then there's going to be discontinuities in the state of the hold, and discontinuities if there's two types of them that alternate. Okay, let's now start thinking about this business of the shared network. What does it mean, a shared network? Shared network means that occasionally when you transmit, someone else may be using the network. If only these two sensors are using the network, that wouldn't occur, right? The protocol makes sure that they not collide. I deconflict them in time. But the point is it's a shared network. So imagine if this is in the car, there's some other feedback loop that's using the same network and it's not coordinating with this one. So it may well happen that at some point you want to transmit to the network, and if this is a CAN bus, someone else is transmitting with a higher priority, in which case you won't be able to transmit, so you'll have to wait. And there's a couple of things you can do. One thing is if you wait until the network becomes available, and then when the network finally is good to go, you could either send the old measurement, or if you have the smart sensor, the sensor just takes another measurement, sends the most recent one. To keep my life simple, I'm actually going to consider the last one, which is in fact in some ways is the smarter one. If you have to, then don't send an old measurement. When the network becomes available, just send exactly, measure it again and send it. Right? Be completely trivial. What's going to happen though, as soon as you do that, is that the difference between consecutive times are going to become variable. You may be trying to sample at a constant rate, let's say every millisecond, and most of the times the difference between the two is going to be 1 millisecond, but occasionally you'll have to wait, and then you may have to wait 2 milliseconds, 3 milliseconds, right? So you have this sample data system where the interval between sampling time is not going to be constant. You have no control over that, right? There's some other external loop that's going to determine that. There's a couple of ways to study systems of this type. There's the deterministic approach and the stochastic approach. In the deterministic approach, what you do is the following. You let the system run for a while, and you keep track of the time between consecutive samples. And then you see, well, I let this run for a day, and I figure out that the interval between consecutive samples is going to be always between 1 millisecond, maybe because that was my sampling time, and in the worst case that I've observed could be 50 milliseconds. And then, if that's the case, you would try to construct your controller so that you will have stability no matter what delay you have in this interval, from 1 to 50, right? And you basically would protect yourself against sort of the worst case sampling sequence that fits in this interval. All right? Another option is to regard this as random variables, and instead of simply looking for the minimum and maximum value in this interval, you're going to keep track of the histogram. Right? And now you have, well, it is true that it could be as high as 50 milliseconds, but perhaps with very, very low probability. And if you keep track of the histogram, you have a distribution. And then what you do is to now design a system that, for this particular statistic, for this particular distribution of the sampling times, you get good behavior. It's now going to be a stochastic system, so good behavior has to be understood in a stochastic way. Perhaps you want the expected value of the error to be small, something like that. One thing that's going to be important in a minute, if you go this approach, and that's really what I'm going to be talking about in this talk, and you look at the histograms of what these things look like, you will observe that you get fairly complicated distributions. It's even the process I just described would show you that's the case. So imagine that generally I design my system to work at 1 kilohertz, right? So in general, I'm going to have 1 millisecond. Most of the times, it's going to be 1 millisecond. Hopefully, the network is not too congested. But then occasionally, I have a tail, which is going to be when I wait. And many protocols would say, well, if you have a collision, wait a random variable with a certain mean and distribution. This leads to this type of distributions. A peak that corresponds to the no collision, and then a tail, which could be, it depends on your protocol. And so it's not uncommon at all to have multimodal, so complicated distributions. I guess the point I'm to make is that you shouldn't expect to see something simple like an exponential or a Gaussian or something like that. You're going to get messy stuff. So as I said, I'm going to talk about stochastic modeling. The main reason is because stochastic model tends to lead to much less conservative results. If you take one of these systems and you observe what happens over a long period of time, you're going to find that with very low probability, maybe if you look at this for 2 days, during these 2 days you're sampling every millisecond, you'll find that at one day someone did something strange, like someone turned on, if this was a wireless, someone turns on a fridge, and the fridge creates electromagnetic fields, and that just causes this huge delay. You're going to find that the worst case is really, really bad, but incredibly rare. If you take a deterministic approach and you just consider even that crazy situation that happened only once over 2 days, over billions of samples, you're going to get a terrible result, right? There's a more, if you want to go for a more theoretical reason why you do that, it turns out that you analyze the worst case behavior, in most cases you realize that the sequences that lead to instability have measure 0, in almost all cases. Right? So you're protecting yourself against something that has 0 probability of occurring. But still, if you're doing worst case, you have to have even 0 probability. It's not even, please notice if I didn't say things that happen with low probability. I didn't say with low probability, I said with 0 probability. The worst case seems to have 0 probability. You know, it's the probability of getting exactly the number 1/2 as a uniform random variable in the interval 0, 1. You'll never get exactly 1/2, right? That's the difference here. Okay. So let me, the model we're using is called stochastic hybrid systems, and let me tell you how you get those. I started deterministic hybrid systems because they are simple, and in fact then there's many ways of generating stochastic hybrid systems out of this. So a hybrid system is a system, it's hybrid because it's a mix of ODEs, so actually each of these circles corresponds to be called a mode. And when you're in this mode, you solve this ODE, your X evolves according to this ODE. But then occasionally you have changes in your system. These are instantaneous changes in your state. And so the way you interpret the system is the following. I'm in mode 1, this Q equals to 1 means mode 1. And if I want to figure out what happens to X, I solve this differential equation. And you keep there until a certain logical condition arises. You know, perhaps until your state, your first component of the state reaches the number 5, becomes larger or equal than 5. At that point, you say that there's a mode transition, you suddenly you move to this particular differential equation, so there's a new differential equation, but also instantaneously you may have what's called a reset, may have a discontinuity in your state. Right, and that's just instantaneous. The state goes from one place to the other, according to a reset map, that's this phi. So these are called guards, it's what determines when you switch, and these are instantaneous changes in the state, and then you also change to a different differential equation. The Q is called a discrete state, there's these modes that change, the X is the continuous state. There's many ways to introduce stochasticity in these systems. This is probably the easiest one, and in fact it's going to be the one that's going to be used in the example I'm going to show you, which is to say, well, let's introduce stochasticity just on the times at which you transition. Instead of testing a deterministic condition, let's label those with some random variables called T1, T2, T3, and I'm going to have a transition when you reach this particular time. Okay? And in this model, these are called stochastic hybrid system driven by a renewal process. They also called time trigger. The way you generate these times at which you switch, these are random variables, so that the difference between consecutive times are independent, identically distributed random variables with a given distribution. Exponential, whatever you want. I mean, they have to be positive. The support has to be positive. You can't have negative times because t plus 1 has to be larger than t, but you know, pick whatever you want. Okay. There's a special case of this that had been studied way before I started being interested in this, which is a beautiful, very complete theory, is when the distribution is exponential. It turns out that in that case you can show that the x is a Markov process. This is very well studied, very nice theory. And you know, being Markovian was it really what helps it. But unfortunately, in the example I cared about, one of the things I told you, not by accident, is that exponentially it doesn't help us. Remember, what we're talking about is a case where you would be doing a certain sampling time and with very large probability. Maybe you even have a probability spike there at a particular time, and then you have a tail that depends on your protocol. It's not going to be exponential, that's for sure. So it's not going to be Markovian. So let me now go back to the system and try to model this as one of the stochastic hybrid systems. That's fairly straightforward. If you remember, the x and p were, well, I just assuming they are linear. So between transmissions, what you have is a linear system. You have this is linear, this is linear. The whole was just an equation y dot equals 0. So that's a linear equation. So you could take all the states of the controller, the process, and of this whole, I guess that's what they call the x. You put them all on top of each other, and between transmissions, you just have an equation which is x dot equals ax. If there was noise, you'd have to put some noise coming in. If there's no noise, it's just a closed loop. By the way, this is not going to be stable, this A, because this is between transmissions, this is open loop, right? There's no changes here, right? So if either the process or the controller was unstable, that A is unstable, and for sure it has the whole. The whole is y dot equals 0, that's an integrator. At least it has an integrator there. Okay, so the A is unstable. The way this is going to then I do this funny thing. I put here two modes with exactly the same dynamics. Why do I do that? Because what's going to happen is that, remember, the idea here was that on the odd instance of time you transmit one state, on the even instant of time you transmit the other state. What's happening then, if you think about what's happening in terms of this state, is that the x and the xp and xc, the state effect control process, they are continuous. There's nothing, no reset being done there. It's just the new value is equal to the old one. The y, sometimes you update the top component of the y, sometimes the bottom component, and the update actually you can write it just as a linear map. You go from one value of x to j times x, but at odd instant of times you have one j, at even instant times you have another j. All right? So I did this trick of creating two modes which have the same dynamics, but these reset maps are different. All right? And then I put here my times at which I have the sampling times. And the system is interesting because each one of these modes is unstable, but if all goes well, when I put this together with the switches, it's going to be stable. Right? What's going to stabilize the system is the switches. And in fact, that's the case if you do this right. Okay, what I want to tell you about here is the result. I chose this particular result to present here because it turns out that there's a necessary and sufficient stability condition, easily to test numerically to analyze the stability of these systems. And at least now, out of this, you'll know how to analyze this particular system and complete answer to it. I'm not just going to give you the test, but I'm going to tell you a little bit about how you get to it. So I'm simplifying my life to try to explain how the test goes by. Instead of considering two modes and two jumps, I simplify this just one mode and one jump. It actually would be the equivalent of that problem. You know, I complicated the problem by putting these two sensors. If you only had one sensor, that's what you'd get. One mode and one jump. You're always transmitting the sensor. The problem is still non-trivial because you still would have an A which is unstable and you're trying to stabilize it through that jump. Right? So a very natural thing to do to analyze this system is to look at this as a discrete time system where you just consider the jump times. right? These tks are random variables, and I define xk equals to x of tk. With understanding and being careful by the fact these tks are random variables. But it's certainly not very difficult to write xk plus 1 as a function of xk. It's a linear system. All I have to do is, I just add a jump here. I solve this equation from a tk to a tk plus 1. It's a linear system, it's just an exponential, matrix exponential. And after that, there's a multiplication by j. So that's the formula. The simple formula for xk plus 1 versus xk. Now, I have to analyze this. I have to be careful that it's a random variable. But I could try to do something naive, which is, if this was not a stochastic system, it was just a regular discrete time system, I would know that there's a quadratic Lyapunov function to it. Right? I'd solve a Lyapunov equation in discrete time, and I would get a Lyapunov function. So why don't I somewhat naively try to do an analysis based on that? Let's imagine, let's take a matrix P, and let's look at the quadratic form involving P at time k plus 1. Right? And so the way to think about this is that I look at my state at time xk, so that's given, and I want to figure out the value of xk plus 1 transpose p xk plus 1. It's a stochastic system, so in fact I'm going to do an expectation here. When you do this, you just have to basically take this expression here, plug it there. The xk's come out of the expectation because I'm conditioning to it, so as far as I'm concerned, these are just deterministic quantities. And this is the formula that I have. The expected value now comes with respect to the only quantity which is stochastic, which is tk plus 1 minus tk. And I'm assuming here that I have a certain distribution, right? So that's the expectation. So once again, I could continue to be optimistic and say, well, let's imagine that I can find a matrix P, so this matrix P is positive definite, and when I compute this expectation, I get something that's smaller than P in the sense, sort of with respect to the positive definite semi-order, right? So it's the difference between this and that is negative definite, right? Let's imagine that I could do that. Well, in that case, I can put here smaller or equal than my original value. So the expected value xk plus 1, p xk plus 1 is in this case smaller than xk p xk, right? Because this pc is smaller than p.
The left-hand side is stochastic, right?
Sorry?
The left-hand side is stochastic.
Not because well, it's conditioned to xk, right? So I condition to xk, right? And this is just expectation, right? It turns out that in that case, you get an inequality that you piece together. And you have to take expectations of that to get rid of this condition. But we'd fairly easily be able to conclude that you'd have actually the limit of the state, the expected value of the state square at this jump times would converge to 0. Would come from this. There are now two things here that are still unresolved. The first one is this only talks about what happens at the jump times. In the meanwhile, remember, in the meanwhile you're solving these equations and the system could be unstable, right? Most likely you're trying to stabilize the system. So between jumps, you have a state that's exploding exponentially fast. So that you have to worry about what's happening between the states. The second thing is that what if it's impossible to find such a matrix P? Maybe I was just asking too much. Is this a necessary condition? It turns out this is pretty close to necessary and sufficient. But you need something extra to worry. You need to worry about what happens between the jumps. So there's many notions of stability here. Well, for now I'm just considering exponentially fast convergence. So this is exponential stability in expected value. Having mean square exponential stability, which means exactly this. Notice now I put now here t, not just the tk's, right? I want to study my whole system. That's equivalent to two things. One is exactly what I had before. This is in fact a linear matrix inequality in P. But that's not enough. In general, you need another condition to take care of what happens between the jump times. And that condition looks a bit funny, but it's basically to guarantee that while you are in between samples and your state is exploding exponentially fast, nothing bad can happen. If the distribution has a finite support, that condition actually is not needed, because finite support would mean that the time you are in this exponential increasing state is finite, let's say 10 seconds. Well, bad things can happen in 10 seconds, but if it's just 10 seconds, it will never explode to infinity in 10 seconds. And this condition, that would mean that this f eventually becomes 1, so when you take this limit, that's 0, it will be 0 after a while. In case you have distributions which have an infinite tail, like an exponential, and I have distribution that with some probability could get larger and larger lengths, then basically what this condition says that you have to look at the tail of the distribution, how fast the cumulative distribution converges to 1. You have to compare that to the rate of explosion of your system, right? And there's this condition, it actually ends up being a condition on the most unstable eigenvalue of A. Very
Are you saying it is sufficient to have exponentially fast exponential decay in the tail to have the limit equal to 0?
No, you need this and that to have that.
No, I mean the last one right there.
The last one, yeah. Essentially, if this is, there's many things that this could happen. For example, if your A is unstable, when you take this product, what's going to dominate is the most unstable eigenvalue, because you're multiplying it twice that. As long as the tail goes to 0 faster than that, that's enough.
Oh, with respect to the eigenvalue.
Yes, you have to compare the tail with the most unstable eigenvalue. That's what you need. The piece of this result that is more difficult is to prove that this is necessary. That this is sufficient, actually, I don't think you'd have too much trouble. I mean, it wasn't very complicated. I did it mostly here, except for this little piece here. The fact that it's a necessary and sufficient condition, that's where the complication arises, and there was a very bright student, Ward, that did that.
Assumption on the distribution of
No.
except for the
In this particular result, oh no, this is general, yeah. I was going to say that we have some other results that don't work if you have probability masses, but this one actually works even with probability masses. So there's no other assumption. There is a technical assumption that I didn't put here, but it's not on F. Yeah, I mean this was incredibly surprising for me, because I knew the result for exponential, and I thought that if you go away from exponential, lose Markovian property, it's going to be a huge mess, and that turned not to be the case. So that was very pleasant.
The second condition.
Yeah.
The left one you can get from the Lyapunov equation for Markovian linear system.
This one?
Yeah.
It's not the same as Markovian. I mean, if it's Markovian, then this would have to be an exponential, yeah. Yeah.
But it's the same.
It's similar, yeah. You could. I mean, that has to be a special case of this one.
The second, what would be the role of the second one? Why would that also play a role? It's just But that would come from the left one. If the left one. Oh,
yeah, it's between samples. This is the intersampling behavior. Yes.
Just to make sure that, okay.
Yeah, I mean, with the samples you don't need it.
It's often true for linear systems that they saturate. Would that be sufficient? Because that means, although the system is no longer linear, but with the constraint, the state never goes beyond some.
Yeah, if you have something extra that gives you that the state cannot blow up between intersamples, then this is not needed. I mean, saturation will introduce other complications here, because then this equation is no longer true, and then this equation you'd have to worry about that. I mean,
But you'd think that would be the key other piece that you need.
At least for the intersampling behavior, yes. Well, I'm going to skip this. It's actually interesting to realize that if you have, and this is also very different than the Markovian case, that if you consider different types of stability, it's going to be so there's many ways to define stability for stochastic. For example, before the one I showed was this one, you want the expected value to converge to exponentially fast, but you could, for example, just want it to converge, just asymptotic, or you want to be integrable. In the Markovian case, these are all equivalent. If you have one, you have all. With general distributions, that's not the case. If you look at the necessary sufficient conditions, all of them have the same piece here that has to do with the behavior at the sampling times, but the necessary sufficient conditions just differ by the intersampling behavior. You have to worry about the tails and what happens to the tails. With some tails you get exponential to 0, others you only get, and these are the conditions. They're all testable, but if you had seen the results for Markovian linear systems, you'd have probably noticed that it doesn't matter what kind of mean square stability you're talking about. Yes?
Matrix J does not appear.
No, not on the condition on the tails. And that's because you're just worried about intersampling behavior, and that's completely determined by the matrix A.
So the necessity is that if it does not hold, then there is a J matrix that
No, there's an initial condition. There's a problematic initial condition. Now, the J is fixed here. The necessity is that if this doesn't happen, then either this fails or that fails. But for a given J, this is not that there exists a J.
conditions do not depend on J.
They do. The J is. Oh, sorry. When I copied from one place to the other, the J is here.
Okay.
Oh, sorry. Yeah, I guess here I did I dropped the J. The J appears here.
But the second condition must
That's no mistake. That it shouldn't be. Yeah, I never realized that I dropped it there. Okay, I think I've said all this. Okay, there will be more to talk about stochastic hybrid systems, but then I wouldn't have time to talk about my talk. But I at least want to tell you that I gave you a very simple version of stochastic hybrid systems. They're all the stochastics within in these J's. There's other classes which are more difficult to deal with, is when the times at which you jump depend on the current value of the state. One way, the particular model that I have here, is this label, the way to read this label is if you take a very small interval, if you have time t, and you look at dt, very small interval time in the future, and you ask, what's the probability that in this small interval of time I'm going to have a transition? That is, well, in general, it will always be proportional to the length of time, but this constant here depends on x. So you may be in places of the state where this lambda 1 of x is 0, meaning this portion of the state you cannot jump. And then you may transition to pieces of your state where this lambda 1 of x grows very much, and then it becomes very likely that you'll jump. Okay? These are more difficult. There's no necessary and sufficient conditions for stability for these systems. We have worked on those too. Then for this you have there's some nice Lyapunov-based conditions to study stability. But like in any nonlinear system, you have to look for Lyapunov functions, and that's always difficult. Other thing I didn't talk about is controller design or protocol design. All those things we've played with them, and I think it's worth to work more on them. Okay, but let me now change gears, because I've been focusing entirely on computation, on the communication part and the modeling of that. I want to just spend the remaining of my talk talking about now using a lot of computation when you do a controller, and I'm going to talk to you about this is much more recent work. Okay, so one perhaps the best well-known method to use heavy computation in a control loop is something called model predictive control. And the idea is that at every sampling time you solve an optimization. Right? And in standard model predictive control, what you do is the following. So this is, you have a process, you measure the state, you want to generate a control signal, this will be a dynamic, some fair stand, and you are at time t, and you hypothesize what you're going to do up to 2t time steps. This is discrete time at this point, although one could do so also continuous time. And you have a certain control objective, and you're going to choose your control signal u from now to now plus t seconds to minimize this control objective. So you solve an optimization like this, starting from your current state and looking forward into the future. And then you get all these control signals from now to now plus t. You apply the first one, or in some cases you apply maybe the first two. Let's say the first one, just to simplify. By the first one, you see what happens. You see where your state landed, and if there's no disturbance, nothing, you land exactly where you expect it to land. But if there's any disturbance, maybe you go a little, you don't quite land exactly where you expect. But at that time, you solve your optimization again with from now to t times in the second. So you have this horizon that keeps receding, and you keep doing this forever. And so you construct out of an open loop optimization, you construct a closed loop feedback system. The interesting thing about MPC, so of course it's complicated because you have to solve one optimization at every time step. So if you're running something at 1 kilohertz, you have to solve 1,000 optimizations per second, right? So let's keep in mind, you'll have 1 millisecond to do an optimization. The good news though is that once you put this as numerical optimization, you can put constraints on my state, constraints on my control signal. You can choose here whatever you want. Maybe I want my my tracking error to be small and my energy to be small. Maybe if this control DC motor, you could try to maximize the energy that goes back into the battery because of the EMF. You can do all sorts of crazy stuff here. It's all optimization. In principle, you could do this for linear or non-linear. The problem makes sense in any context. Of course, there are some difficulties here. The first one that becomes immediately clear when you start putting non-linear constraints is that you will have to design pretty efficient control algorithms, right? Because you have very little time. In this version that you see here, you have to know the state, because the idea is that you look at the state, you optimize from there. And the last thing here is that what you're doing is solving these optimizations, but you actually never apply the controller. I mean, you apply the first one, and then you redo the optimization, you're going to get something slightly different. Even if there's no noise, you'll get something different because you keep receding your horizon. And so, will this lead to something that actually converges to anything? So those are the complications here. There is a version of this which I'll introduce now because I'll need it in a little while, is that there's a version of this also for the case of disturbances. And this is in the case where there's some disturbance, you don't know quite exactly when you apply certain control, a certain state, you don't know exactly you're going to be because of a disturbance. There's a thing called the robust MPC, where you minimize over your use, you try to protect yourself against the worst case disturbance. And so you have to solve a min-max problem. Sometimes you put some penalties here that are basically going to sort of penalizing very unlikely disturbances, right? When you start putting a maximization here over disturbances, if you don't put any constraint, you could just get a crazy disturbance there. So it's not uncommon to put something that penalizes the likelihood of disturbance. So you put here a minus sign so that the maximizer is kept from doing crazy stuff. That's min-max MPC. Okay, now what I want to address is still this challenge here, full state measurement. That's where we've done some contribution here. So what if you don't know the state? The standard approach when you don't know the state to use MPC is that you build an observer, some sort of state estimator, and then you just take the state estimate and you use it in your standard MPC as if it was a full state. In this vein of our constructing observer, there is also one version of state estimation that's very good at using computation. It's called moving horizon estimation. And so this is now just an estimation problem. Eventually I'll come back to the controller. But what this moving horizon estimation does is it looks at the process, looks at the inputs and outputs, and there's some disturbance and noise that you don't know. And moving horizon estimation tries to find what is the estimate of my state that's most likely in view of my observations. So you maximize the likelihood of particular sequence. You don't know the disturbance and noise. You try to maximize the likelihood. Try to find the sequences of disturbance and noise that are most likely, in a statistical sense, subject to the constraints of my dynamic and all the observations that I collected over a certain amount of time. And to make this a practical problem, you only look at the last 10 seconds of data. Right? At any point in time, you just look at the last 10 seconds and figure out. So this is, in some ways, it's completely standard maximum likelihood estimation, with the caveat that you're going to eventually look at the last 10 seconds. So you could always, every time you throw away a little bit of the distance passed. What is interesting about this particular formulation is because you reduce this just to a numerical optimization, you can put constraints, very much like in MPC, you can use nonlinear systems, you can have very sophisticated noise models. Of course, if you were putting here, if your distributions were Gaussian, when you compute log likelihoods, that's going to be quadratics, that's great. But if you're willing to solve more complicated optimizations than quadratic optimizations, you can put whatever distributions you want there. Of course, once again, if you put a complicated distribution, you end up with a complicated optimization problem. But if you're willing to solve complicated optimizations, that's fine. So this is just to say that if you have the noise and disturbance independent over time, what this likelihood estimation looks like is basically going to subtract the log likelihoods of your distributions. In case of Gaussians, you'd be maximizing minus squares of that. So this is what, so in practice, this moving estimations look like is this. The problems are maximize, you hypothesize over disturbances and noise, some summations over past. See, I'm at time t, and I look at the likelihood of my noise and disturbances up to t minus L. L is my horizon, my backward horizon. Okay, so this is now the stuff that we've done. One way to think about this is that we put all this together. Instead of solving first an estimation problem and then get an estimate and then using that for control, we're just going to construct a large optimization that will do everything at the same time. So let me sort of guide you through this. So this piece here is something that goes from t to sometime in the future. So I'm looking at the forward horizon. And I would like this performance to be small. Very much like MPC. And I have a minimization over U, over my future use. But I don't know my initial state. All I know is some past measurements. So I'm going to solve one of these problems. I minimize over U, and I maximize over all the things I don't know. I don't know my initial state, I don't know my disturbance, and I don't know my noise. Right? I do have some constraints. I have dynamics as a constraint. Maybe I know sets, maybe this disturbance, I know my noise is quantization noise, so I know exactly where it lives. But I'm also then going to put this penalty on likelihood terms. This is exactly the same kind of things that you do in likelihood. You penalize the likelihood of a particular value for a disturbance and noise. So in this problem, it's an optimization, lots of stuff going on here. There's some parameters, which are not optimization, but just parameters. This is my past inputs and measurements. Those are going to be part of my constraints, or we're going to constraints of this type. Because I know a y, and I'm trying to estimate x and n. The optimization variables are going to be, for the minimizer, my future control signals. The past ones I've chosen, I can do nothing about that. And and then the maximization variables are my initial state at the beginning. See, I go back up to t minus L, my state right when I started. I'm going to maximize over that. The disturbances, I'm going to have optimization variable, for instance, both for the past disturbances, because they affect my value of the state from my initial to now, and my future disturbances, because they're going to affect my future criteria. And past noise. I haven't measured any future noise, so the noise doesn't appear here. So I also have as optimization my past noise, which in fact I forgot here from this list. There should be a 5-bullet item there saying past noise. So this is just a picture of what happens. At time t, I know my past input, I know my past y, and then all these dashed things are things I'm optimizing over, either maximizing or minimizing. Of course, now one could ask, why would one, instead of solving these two optimization problems, one for estimation and one for control, why would it solve a larger optimization problem? Because in almost all problems, solving two small problems, I mean, as long as complexity is worse than linear, solving two small problems is better than solving a big problem. All right? Just out of linear, any complexity. And there's two reasons for that. One of them, I guess, is a theory related to the answer related to theory, is that if you do it this way, you can prove stability of the system and convergence. It's an interesting answer. The practical answer is that this approach protects you against optimistic state estimates. You see, in general, my estimate is going to have some error. If you do it in this way, you're going to, among all the equal likely possibilities for my state estimate, this one is going to be worried about the worst of them. Taking into account worst in what sense? Worst in making the performance as bad as possible. So the state estimate takes into account what I'm trying to achieve and worries about the one that will lead me to the worst situation. Okay?
I think there's another advantage.
Okay, maybe. Oh, I would love to know more.
If you couple the control and the estimation, it may happen that you can do something with the control that will improve the estimate. It's the central idea in adaptive control.
Yeah, but you know what's the problem with that? I would love to have something to say, is that this will not catch that.
Why not?
Because when you solve this optimization, you don't take into account your measurement equation for the future.
I see.
And that will only matter if that. I would love to. I have some ideas on how to do that, but the way it is now, that would be a wonderful thing, but this is not doing that.
I don't want to argue with you.
Yeah, but yeah, if I could understand that better. I'll tell you a little bit more about that. For now, the way to think about it is if you have some model for these disturbances and noise are coming from, you saw some stochastic model, you choose it based on that. In practice, and I'll tell you a little bit more, you have to make sure those are reasonably large. So I'll get back to that, okay? Anyway, so we actually have a paper in the context of specific problems that we actually show that it's good to do these things together. Not for the reasons you're saying yet, because that I would like to know much more. I'd like to figure out. I think that's a great problem, but I don't think we really have an answer. By the way, you'll notice the biggest differences between doing these things together and separately if you have problems that have asymmetries. Where we did that in a problem related to insulin control. And it turns out that in positive errors are much worse than negative errors. But the estimator doesn't know anything about that. Right? The estimator is just trying to find the most likely. He's not worried about that. If you make an error in the positive direction, it's much, much worse for a person than if you do it in the negative direction. And then we gain a lot by doing this. Okay, so I'm not going to do any proof here, but I do want to talk to you about what are the assumptions that you need to do this proof, which I'm not going to show you because they are useful. All right, so there's going to be three key assumptions. Two of them very natural, and the other one more unusual. One assumption, if you have seen model predictive control, is a common assumption. It has to do with the terminal cost that you put here. If you think about this terminal cost, so you're doing a cost, you look at some time in the future from t to capital T seconds into the future. And then you also have a terminal term that the idea behind the terminal term is trying to capture what's missing from that summation. You want to make sure that you won't end up in a very bad place. Right? But every time you do this reseeding, you're going to get another term in your summation. And you have to somehow take care of that in your proof. And the standard way to do that, or one way to do that, is to ask this thing to be what's called a controller Punov function. It's, as I said, if you had seen MPC, you've seen almost all the papers. There's two ways to do these proofs. Either you do a terminal, either you put a terminal cost or you put a terminal constraint. Terminal cost typically is more robust. So that there's not a lot to be said. I could say that to be able to find such a terminal cost, you need the system to be controllable. This would prove controllability. And it's quite natural to expect that you're solving a feedback control problem. You want your system to be controllable. So this is a controllability assumption. The second assumption is going to be an observability assumption. If this was a linear system, this I could just write observable. But this is non-linear. So I have to say it in there's a somewhat convoluted way. Basically what you need, you're only looking at you're looking at past L measurements. You have to be sure that based on the past L measurements, you're able to reconstruct the state with some accuracy, right? In a discrete time system, what that would mean is that you need observability and you need to look typically the size of your state space. If you have a system of order 5, you need to look at 5 steps into the past. In some cases, you may not need all 5. The way this is stated here is it's also about the horizon to be longer, a little bit more. So imagine that you look at a trajectory over L plus 2 times into the past. You look at this whole particular trajectory of the state, inputs and outputs, L plus 2 into the past. And then, of this L plus 2, pretend you don't know the state. And pretend you don't know also the most distant past input and output. So now you just got L plus 1 inputs and outputs. And now construct a state estimate out of that. So look at the set of all state estimates that would be compatible with those L plus 1. Right? So you consider state estimate. And now bring back the input and output that you left behind. Remember, I told you start with L plus 2, then put aside the last one, bring it back, and look whether or not you're getting something that's consistent with the one that you brought back. And this assumption is saying, yes, all the possibilities have to be consistent with those two. So if you have L plus 2 and you forget one, by forgetting that one, you're not losing too much. Okay, that's what this is about. It has to be stated in a rather convoluted way because we're trying to do this very general for nonlinear systems. So it's not as simple as some sort of rank condition. If this was a linear system, this is just observability.
So if I give you a F and G, what are the conditions that need to be satisfied for this stuff?
If they were linear, this is just observability. If they are non-linear, I don't know. This is if you were local, probably you could look at these conditions, geometric control theory conditions for observability. That would be work, but we're trying to make global results, and that's why if you're trying to do this global nonlinear, we don't know of any sort of nice algebraic condition to test this. Right?
Do you know nonlinear cases where it's satisfied?
It's straightforward to come up with examples, but if you give me a system, whether or not I'm going to be able to prove it, it's a different story. It'll probably be very easy for you to give me something I won't be able to prove it. Okay?
So the answer to my question was yes, there are.
There certainly are systems where I can.
Nonlinear for which you can prove.
Yes. The answer to that is for sure there are. Okay, but there's a third assumption, which is neither controllability nor observability, and that is. Make sure I'm not. Oh, I'm going way over time. Oh, I apologize. And the other convention is actually this min and max have to commute. That is, to be honest, much more mysterious condition to me. We know exactly what it means in the linear case. It's observability and making this rho and eta sufficiently large. You have to penalize them. Right? You basically can't leave too much freedom to this here. So we prove this for the linear case. It's still a little bit unclear. In general, and I'll show you some nonlinear results, it boils down to choosing these penalty strongs. I'm going to skip this. The proof. The other thing we get out of this min-max commuting is we get for free a numerical algorithm that allows us to compute this very efficiently. Let me tell you what I mean by efficient. This is an 8-dimensional system. It's a linear system. Look at the solve times. One optimization, 3.2 milliseconds. Hundreds of variables. This is linear quadratic. Everything is convex and concave. We've also done this for problems which are not convex and concave. We can't prove anything out of this, but we can solve the optimization. This is a non-holonomic pursuit. This is a vehicle that you can only choose direction, fixed velocity, trying to pursue an integrator. This kind of it's homicidal chauffeur problem. That's another version of it. We actually implemented this, but look again at the times. 2.6 milliseconds, 5.0 milliseconds on a laptop. And we can even do things where we have disturbances which are, in this case, disturbance is the evader, but we also put wind on it. And now we also consider worst case winds, and you get all sorts of trajectories here. So anyway, this was a little rush because I was answering questions, I lost track of time. I apologize for that. But going back to my original slide, so I wanted to tell you a little bit about interesting things that happen when you put networks in control systems. And once again, there are chips now that allow you to do that in a very inexpensive way. And there's lots of interesting things you can do when your control nodes have lots of computation power. Right? And it really opens the door for all sorts of interesting ways to do control and estimation, as I showed you. So that's it. Thank you very much. Some addition? Yes.
One question regarding your network control analysis. Using your analysis, if my objective is to design a control game, how would I go about using your analysis on Stochastic?
It's a little tricky. It's a little tricky because I'll tell you what the problem is. We have done something, but at the loss or at the price of losing necessary and sufficient conditions. The A matrix appears in this condition in the exponent. So, for example, imagine that you're doing state feedback and you want to put there an A plus BK. Unfortunately, the BK appears in the exponent. On the other hand, if what you're trying to do is designing, for example, what to send is J, it's a little better. Right? It still appears as a quadratic here on P, but it's better than the exponent. So it depends a little bit on what you're going to do. But probably I would not use this formula. There's other formulas that you could use. They're not necessary for stability, but more amenable for control design.
Now, people have tried to design the network using these analysis conditions. But then the question is, isn't it conservative if you are not changing your feedback A and K, and you are just using the stability analysis to design the network? In the sense that it might be possible that... Absolutely. What you want to do is design both at the same time if you can. Absolutely. So is there any approach to design both the network and the feedback game?
What we have done was not so much designing the network, but what we have done is co-designing of the controller and the communication protocol. That's another thing that you can do that you gain a lot. We have not done anything about also changing the network, right? But that's interesting, obviously.
And you said there are two approaches. One is deterministic, one is stochastic.
Mm-hmm.
So in terms of designing the controller, which approach do you think is more?
I think that a stochastic approach will give you less conservative results, and in some cases easier results than the deterministic ones. That example that I've shown you there, that little toy example, I think, there are no known necessary and sufficient conditions for stability in the deterministic case. So I would not be able to give you, no one knows, even for that very simple exact example, tell you exactly what would be the largest interval. There's several papers that use, on benchmarks, each paper proves that they can enlarge the interval a little bit more, but that problem is open in the deterministic case. In the stochastic, now we could compute exactly.
So just one last question. Like many people in computer networks, they say that the successive intervals are not independent.
Yeah.
So how do you?
Yeah, that problem is not too bad. What you do there is, in general, consecutivity is not independent, but a simple model is to say that you have a Markov chain, and that you can apply it. Those results apply with that.
Many assumptions on the Markov chain, they assume finite states of Markov
Yeah.
chain.
Yeah.
So
Yeah.
is there any experimental way to determine if the successive intervals are independent or not?
Well, there are statistical tests for independence. Yeah, I mean that's just to figure out if they are independent. Yeah, with experimental data, there's statistical tests for independence. Yeah, that in principle there is. Yeah.
Interesting questions. Is it reasonable to think that in a more general setting, this J might not necessarily be time and rate, or for example, when you have a communication network over which you don't have high fidelity, where you might have, say, a wireless network, traffic problems?
Yeah. So actually, nothing. If you'd make this J stochastic, you could also take an expectation against that. Yeah. The only thing I don't know is if then this condition is necessary again. Sufficient for sure it would be. Whether it's necessary, that I don't know. I don't think we looked at that. All right. I think I kept you here long enough. Thank you.